Hi, class. So today we're going to finish off the chapter on recursion with discussion of a single algorithm. The section 5.4 is about recursive algorithms, and we've kind of already spoken a little bit about it. But I want to focus today's lecture on merge sort specifically. So that's the only thing we'll cover, and that'll be the end of chapter 5. And then starting on Wednesday and for the following two classes, we'll discuss chapter 6 on combinations and permutations. Okay, so merge sort can be written in any language, really. The algorithm is language independent. So the idea is that it's broken up into two steps, and so this is the Java implementation. Second, we'll take a look at JavaScript. And so it consists of the merge operation, where you take two arrays and you squish them together. Basically, you have a left part and a right part, and you do it in a clever way so that you go down the line, taking the next item in sequence each time, and it can come from either the left array or right array, so that one array has all small items, or the other array has all of the smaller items, like 1 through 5, and the other one has 6 through 10. Or reverse, or it could be some jumble of them. But the idea is that by the time you get to the merge operation, you already have two sorted lists, and so it seems like it's not really doing anything, and it isn't without its other half, the sort operation, which kind of handles the work of breaking it down, and so this is a method known as divide and conquer. But you take the entire collection and you break it up. So if you have 10 items, which we'll see in a moment, if you have 10 items such as this, then you break it up to where you're dealing with arrays of size 1. Like, you break it all the way down, and so you have, instead of one array with 10 elements, you have 10 arrays with 1 element. And then the work of merging them becomes the work of merging these first two elements, so 8 and 2. And then 2 is less than 8. So in the merged array that gets returned, you have an array of 2 elements now that are each sorted, and then that gets compared to the next coupling, right? And so 4 and 6 get merged into an array of 4 and 6, and so whenever these 4 elements get merged into a single array, you'll have 2 and 8, which was the result of this original comparison, and 4 and 6, which is the result of the second comparison. So obviously in that sequence, you pull the 2, and then you pull the 4, and then you pull the 6, and then you pull the 8. And so the breakdown happens here, right, in this merge sort method. And the recursive part, where the function calls itself, the function refers to itself, happens here. Walking through this, we've created this array of items, and then we print it out so we can see what's happening, and then we pass it to merge sort, and magically it spits out the collection of sorted items. But the work that happens in merge sort is pretty subtle, right? At each step along the way, if we have an array that's larger than 1 item, then we break it down, because we can't actually begin the process of merging until we've finished the work of dividing, right? So in divide and conquer, we cannot conquer until we finish dividing. And for this algorithm, we divide it all the way down until we're dealing with arrays of just a single element. Until we get there, we break it up in half, and we just take the left half and the right half. And then because this isn't fully broken down, we break up these 5 elements into the left half, so index 0 through 2, and then the right half. And then because the left half again, after the second call, It's still not fully broken down. We break it up into the left half and the right half, and so we get this and this, but this isn't fully broken down, the left half, and so then we'll do that. And so it'll complete the left branch every time because this gets invoked first, and this operation doesn't get called until this returns, right? So so that original collection of 5 doesn't actually get sorted the original collection of 5 doesn't get sorted and integrated until the sub-collection of 3 and the sub-collection of 2 are returned. And so in that instance, 8 and 2 get sorted into an array of 2 and 8, and then it'll return, and merge sort right will get called, and that'll return instantly because after breaking this in half, we get this as the left half, and then when that gets broken in half, we have this and this. And so then we'll end up with an array of 2, 4, and 8, and it'll want to be merged with the array consisting of elements 6 and 9, but those have to be handled separate because they are the right half, and then that gets broken into the left half or whatever. And so these first 5 elements will be sorted, and then it'll unroll all the way back to the top level, and then we'll have a sorted left half, and then it'll do the same process for the right, again, now breaking it up into left and right, and then again left and right, and then the single elements, and then it'll return and it'll merge this left half with this right half, so that we have these 3 elements in an array, and then it'll deal with the right, which at that point will be broken up, then compared in the merge operation. So what I want to focus on, and the only thing that I really want you to grasp, well, it would be wonderful if you grasp the entire algorithm, it's that this operation happens by breaking up this larger collection, and it breaks it up until we have something that we can manage, and the elementary operation that we're using to manage is a simple comparison. Is left less than right? So is the element that I'm looking at on the left less than the element that I'm looking at on the right? And if you think about it, that is the concept of an ordered set, a sorted set, is that every element in the sequence is less than the one that follows it. And if that holds true for every element, then the array is said to be sorted. And so it makes sense that in achieving this, that is the operation that we use. And that happens, that guarantee happens right here. So if left is less than right, then pluck that and place it into the merged collection. And if not, then that means that the right one is less. And I know what you're asking, like, well, what if there's multiple elements? Well, then we still have achieved a sorted collection, but if there's a tie, then we take from the right, and that just has to do with the fact that of the way we've written it. We could change this to less than or equal, and it would still follow that same guarantee, but it's not extremely beneficial to discuss these edge cases whenever we're trying to grasp the concept of merge sort or the algorithm, but it is necessary whenever discussing correctness. So is it handled? Does it break on this edge case? Well, no, it doesn't. But we don't have to do anything special to treat it due to the simplicity of this and the way we would define a tie in this case, or the correctness of how to resolve a tie. We happen to get that one free in this algorithm. Okay, so let's take a look at the algorithm in JavaScript. So this is a JavaScript implementation of it. And as you can see, the algorithm, as I promised before, is going to be language agnostic. And it really deals with 2 parts. There's merge sort, which is the recursive call and handles the work of breaking down the items and calling sort. And the recursive call and calling merge, pardon, and then the merge operation, which handles the actual comparisons and the heavy lifting of combining this large collection of small arrays and combining them back into an array equal in size to the one that was passed in. And so here we define the items that we're going to pass in, and it's the same collection that we're dealing with here. And then we receive our sorted items as output from our call to merge sort. And so again, we've fully divided prior to conquering our collection if our array has exactly one item in it. And then if not, then we define a midpoint, and it has to be an integer, otherwise the index of like 1.5 is not a valid index. So we have to treat that edge case, and so here this is the equivalent of casting it into an integer. And then we define our left and right arrays, and until and including the midpoint, we push our items into the left array. And in JavaScript, we call push. In Java and C and C#, whenever dealing with arrays, we have to declare the size of it, and that's why we have this syntax over here. But in JavaScript, it's sufficient to define an empty array and then push them onto the end of the collection, and JavaScript will maintain that for us. And then after the midpoint, and then we push the items into the right array. And so this is the division part, right? So we're dividing it in half. We're taking the left and we're dealing with it separately, and we're taking the right and dealing with that separately. And then once it's the smaller collections have been handled, once it returns to a certain level, then we call merge on the larger collections. And you'll see that if you step through it, that the first time merge sort is called, the array is size 10, the second time it's 5, the third time it's 3 and 2, and so forth. And so it's as if the program puts a bookmark, a placeholder, and says, okay, well, once this is resolved, then we can come back and we can resolve this properly. But until then, until these smaller problems have been handled, and the smaller problem being sorting the smaller arrays, we can't do anything with it. And so that is the concept of a stack. If you've never heard of a stack, it's a data structure which resembles kind of like a stack of plates. So if you're taking dishes out of the dishwasher and you're placing them into a cabinet, you'll place the first dish on the bottom, and then you'll place the next one on top of it, and so forth. And then whenever it comes time to eat and you start setting your table or whatever, you pull from the top of the stack. And so this is very much different than a grocery line, or a queue in a grocery store, or a line in a grocery store, where the first customer in line is the first one processed, right? It's kind of the opposite. And so we say that a stack is first in, last out. So the first dish placed in the cabinet is going to be the last dish that you use when setting the table. And grocery store line, or queue, is first in, first out. So first come, first serve, right? In recursive algorithms, these placeholders they follow the pattern of the stack of dishes, where the first call is going to be the last one handled whenever you're calling something recursively. And we actually call it a stack. We call it the function invocation stack, or the program stack. And whenever they start returning, once it's finished dividing and the conquering begins, then it's called unrolling the stack. And so it goes back to that very first invocation, and then it finally gets handled. And so even though merge sort is a recursive algorithm, there's only one recursive part in here. Now, it's called twice, but it happens in the same line. And so, but merge sort, this method, is recursive, but merge itself is not. Merge simply applies the guarantee that the ordering happens. And if we wanted to sort from greatest to least, then our condition here would be reversed, right? So we would take from the left first if it was greater than the right. Okay, so that's the only thing I wanted to discuss today. It's really the perfect example of a recursive algorithm. It algorithmically it has a runtime of n log n as it scales up. So if you were to add, if you had a set of 100 elements versus a set of 1,000 elements, then you would expect the number of total operations of actions taken to scale at the rate of n log n. So 1,000 is 10 times 100 clearly, but the runtime difference between them would be the difference of 100 times 2, which is 10 squared or log of 100, right? Versus 1,000 times 3, and so it's super linear, but it's not quadratic. It's basically as good as you can hope to do in most cases. And so all of the programs that you write as you go forth and you do your great actions, you'll want to aspire for an algorithm that's either on the order of n, so something that's linear, or n log n. And it may not always be possible, or it may just be yet to have been discovered in some cases. But if your algorithms are in that range, then you're typically doing pretty good, or as good as possible. So, all right, no homework today. There's still last week's assignment, and you'll get your next assignment on Wednesday, and we'll begin discussing the final chapter that we'll go over, and then from there it'll just be lectures on the art of programming, basically. Okay, have a good evening.